now that we have an idea of what the adjoint is, we'll look at some properties of it. So first off, if T is a linear map from V to W, then its adjoint is a linear map from W to V. So in the last clip, we already said that it's a map from W to V. So the only new content here is that it's linear. Okay, so let's see. So let's take W1 and W2 to be elements of, whoops, W. And let V be an element of the vector space V. All right, so then we need to check things like additivity. So what's T star of W1 plus W2, for example? So the way we understand this is we put it in the inner product and we check how this works for a given V. And so, by the way, when I said let V be an element of V, I'm not necessarily assuming that it's fixed. Well, I mean, okay, for the moment we'll use a fixed V, but then we'll see that it doesn't matter what V we choose, so we can allow it to be any V, the usual thing. All right, so let's see. So first off, well, what can I do to manipulate this expression? Well, your first temptation might be to distribute it over this sum right here, but we can't do that because it's actually what we're trying to prove, right? So then the only other thing we can do is take the t and put it back on the other side. So by definition of adjoint, this is TV W1 plus W2. And so now you can kind of see what to do. You say, oh, all right. Now that we know how t works, because t is a linear map, and we know how the inner product works, in terms of sums, we can just sort of go to town and break things apart. So this is TV against W1 plus TV against W2 using linearity of the inner product. And then for each of these, I can now move the t back to the other side. So I've got V T star W1 plus V T star W2. And now, since the thing in the first slots match, then I can use linearity again to combine these. They both have a V in the first slot. And then in the second slot, I have T star W1 plus T star W2. Okay, and so here once again, we have, this is all, these are all equalities of numbers, but since this is true for any V in V, then we can extract and say on the level of vectors, T star W1 plus W2, whoops, must be equal to T star W1 plus T star W2 as vectors. And then that's the equality that we need for seeing that the map, the adjoint, is additive. Okay. And same thing for a scalar lambda. Let's see. If we put T star of lambda W in the inner product with V, then same thing as before. The first thing we do is we move t over to the other side so that everything is a known object. And then we can manipulate the expression till the cows come home to get what we want. So let's see. So I can pull out the lambda so it pops out with the conjugate. We have t v w. And then I guess I can put the t back on the other side. So it's V T star W. And then I can put the lambda back in. And that, since it's going into the second slot, it'll change, the conjugate will cancel. So I mean, this is like double conjugate, right? But the double conjugate of a complex number is just the original complex number again. And so that since this is true for every v, that implies that t star lambda w equals lambda t star w. And so that gives us linearity. All right, so that's linearity of the adjoint. So let's just say what we just showed here was linearity of t star as an operator from w to v. Now in the next one, what we're going to show is linearity of the star. So if we define star as a transformation that takes linear maps from v to w and turns them into linear maps from w to v. So star of t is t star. It's the thing that takes an operator to its adjoint. Okay. Then star is an isomorphism, except not quite. So it's an isomorphism that is its own inverse, actually, just like conjugation is, except that if I do the star of a scalar multiple, then instead of getting the scalar multiple of the star, it comes out with a conjugate. So the so this is, for a true isomorphism, it would be lambda star of t, right? So a thing that has this property, if you do it twice, you get back where you started from, and it's an isomorphism, except you're off by a conjugate right here. Okay, so its own verse except for this fact right here. This is called an involution. And the two main examples are conjugation is an involution, right? Conjugation is linear and everything else. And then adjoint. Okay. There's other examples, but they're a little more exotic. So to say that this is an isomorphism, this means that all kinds of the usual properties hold. So for example, if we do s plus t adjoint, that's s adjoint plus t adjoint. And if we do lambda t adjoint, we get lambda conjugate t adjoint. And so this part about it being its own inverse is that, you know, s adjoint is s. And we also have that if w is equal to v, then the adjoint of the identity is just the identity, so it doesn't do anything to the identity. And then the last thing, which doesn't have to do with it being an isomorphism of vector spaces. So additionally, if we take a product, so here that's a composition of operators, and we take the adjoint, then this ends up being the composition of the adjoints in the reverse order. Okay. Now, in order to prove all of these various properties right here, all of these come by the technique that we did above, and that is that you look at some expression that's got the adjoint on one side, you immediately move it to the other side, and then do a bunch of manipulation. This is a common way of working with adjoints. I'm not going to deprive you of the joy and fun of working through these problems. This makes a perfect exercise because pretty much it's just very basic, simple manipulation. Also, you've got the book as a guide, so you can definitely look at the proofs there. But I encourage you to just go give it a shot. Put the T on the other side, and then bang, 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 and then put the T back as the adjoint. Put the T on the other side, and then bang, 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 and then put the T star back as the adjoint. And you should be able to prove all of these guys. Oh, and this one. Probably on your first try or close to it, I think. So yeah, I don't want to deprive you of that. So I'm gonna leave those proofs for you to do. By the way, one handy example or application of this this isomorphism-like property, this involution property, is that if we do T minus lambda I and we take the adjoint, then according to these rules, we're going to get adjoint T minus lambda conjugate I. And so you can see how that follows from these properties. That will be useful for us when we go to look at the eigenvectors of the adjoint and how those relate to the eigenvectors of the original operator.